Okay. Good afternoon, everybody. Today, I would like to talk about aerodynamic, unsteady aerodynamic. I want to emphasize that the present, my point of view, is not the point of view of fluid dynamic people or aerodynamic people. I will emphasize some basic theoretical issue on aerodynamic, but the scope, the final scope of this discussion on aerodynamic is not the aerodynamic itself, but the final scope of this discussion, of this lecture, is to provide an aerodynamic operator. So keep in mind, today I will talk about thermodynamics of fluids, but the final scope of this discussion I'm going to start is to provide a, for example, an aerodynamic operator in Laplace domain. These here are the model coordinate, and what I want to provide is the following practical aerodynamic operator like ES here applied to my model state plus eventually
Professore, non credo che stia condividendo lo schermo.
Yes. I'm sorry. I apologize for this. I forgot to share with you my screen. Okay. So, the final scope of this discussion on a state aerodynamic is to provide this operator here, which is the also known as generalized aerodynamic force, also known as GAF matrix. This matrix, just like the inertial operator or the stiffness operator, is a matrix actually representing an operator such that if you apply this on the state space variable, you should have this final force. This here, or this is E bar forcing term, but forcing is in quote because we will be able to express this generalized load as function of the state space variable Q bar. Note also that I have emphasized Q bar in the sense that I have in mind to represent the displacement, the physical displacement of the body as summation of psi bar shape function on Q bar. Modal coordinate. This means modal. Okay? And before introducing and building the theoretical background for having this operator, I want to share with you the following point. Why model? This is important for your life. Why model? Coordinate. By the Lagrange equation theory, you realize that you can choose the coordinate. You can choose the shape function, and correspondingly, you have Lagrangian coordinate associated to the shape function. This is a choice. The natural choice is the choice of finite element. The Lagrangian coordinate representing currently displacement. And this should be natural. But I show you that you can also use the modal coordinate, which means introduce this modal coordinate in this way, or equivalent in this way. Now, where this part here are the shape function of the finite element, and these are the modal coordinates. So modal means use this and this. And physical, they are not physical at all by me, but some people call this physical coordinate in the sense that this discretized quantity are representing the physical displacement. Okay. So the point is, why I want to use this coordinate in aeroelasticity, and this is standard in aeroelasticity. I show you, for example, the analytical exercise of Panel Flutter. We use modal coordinate because we use the first two natural mode of vibration of the panel. And we wrote the equilibrium equation for these two generalized coordinates, the model one. The point is a question of having a reduced order model as reduced as possible. Okay? And the key for interpret this point is the following. The key is the following. We discussed at this point, but I want to recall, I want to emphasize this. If you express the displacement in your final coordinate, in finite element coordinate, you have this representation, you have the finite element mode shape function, and the finite element degree of freedom. But this summation is a summation from 1 to the number of degree of finite element degree of freedom. Okay? 1 million, 2 million. But if you use this, for example, if you use this equation here, you have that this summation is equal to psi n again, but instead of this you can use another summation. This is n, and this is m, like Milan, and for expressing this coordinate as summation of m n on q bar m. So I substitute this with 1. Okay? But if you perform this summation and if you sum this here on n, you have this here. And so, at the end, you can write this as equal to summation of m from 1 to number of modes, from 1 to number of mode psi bar m on the new coordinate like this. And so here are the two possibilities I have in terms of coordinate. So how can I choose my choice here? The choice is based on the convergence of this summation, the speed of convergence of this summation toward the exact solution. Okay? What I'm introducing to you is an error. You can define error. If you call this as the true quantity, and this here you have almost equal, and this here the approximated one, okay, this is approximated, and this is approximated, u approximated by finite element, and this is u approximated via model coordinate bar. Okay, so you have an error. The error is, you can define the error in several ways. For example, a way for defining the error is a global error. A global error is something like this: the true value minus the approximated to the power 2, the amp modulus of this physical quantity, and then integrate on the space domain. This is a scalar error. This is a global error. Global. Global error is this here, global, like G. And you can define this error for the finite element approximation and for the model approximation. In identical way, you can define a local error. Local error is simply the difference of this quantity in a point. And this is a modulus, and this is a local error, E local. So you have two errors. And the accuracy of the solution with respect to these two errors is different if you consider the approximation given by the mode or the approximation given by the finite element. If you fix the global error as a threshold, for example, E 10 to the power minus 4, the number of coordinate, modal coordinate, for reaching this accuracy is equal to 10. If you having fixed this threshold, the number of the degree of freedom for reaching this accuracy in terms of finite element degree of freedom is equal to 10 to the power 5. Okay? This means that in this case, for having this global accuracy, you need of 10 equations, 10 Lagrange equations for elasticity. In order to keep the same accuracy, you have to consider 100,000 Lagrange equations. And this is the difference. The point is, but the point is fundamental. Is the elasticity a global phenomenon? Yes, it is. And so you are authorized to use this representation because you are representing a global dynamics. Okay? In terms of global error, this is correct. Okay, but if you fix a threshold level as local error, because you are interested to, for example, to represent the stress concentration in the root of a wing or in a point of your structure, in a critical point of your structure. In that case, if you fix E local as equal to 10 to the minus 4, the number of degree of freedom in terms of finite element is again 10 to the power 5, but in order to represent your solution in that point, you need also to the number of modes equal to the same order of magnitude. So the maximum possible number of modes you can extract by your model. Okay, and this means, excuse me, and this means that if you have a function with a critical quantity, critical means that, for example, the stress in that point has a gradient like that, an important variation of stress. And if you use the modal superposition for representing something just like discontinuity, but discontinuity may be also a high level of gradient of the quantity. I use the stress, but you can use the displacement and so on. For representing this discontinuous, how many shape function, global shape function you need for representing that discontinuity? You can superimpose. Remember that your solution is the superposition. Imagine you have this beam, for example, and you have the first mode is something like this. The second one is something like this. Excuse me. The third mode is something like this. How many waves you need here to represent this? Remember the Gibbs phenomenon in Fourier. This is just a Fourier. The orthogonal superposition of the mode are some identical to the Fourier series in a time domain or in a space domain. You have in the window an harmonic function. Forget the fact that this window is replicated, you don't care, but inside that window you have a function to be approximated. If you have a discontinuity inside, you have to use many terms. And these terms are the mode, space function, just like the sine cosine. It's identical concept. So if you have a concentrated load giving you a gradient, high gradient of the output quantity, like the displacement, like the strain, the stress, you need many modes. And you have a paradox. You have to use some mode how coordinate you have. So the maximum possible number of eigenvector. The maximum number of eigenvector is equal to the number of the original variable, in theory. Okay? And so in that case, in the case you are interested to minimize a local error, the modal approach does not work. Okay? And this point I have mentioned is a comment in space. You have identical comment also in time, because with the modal analysis, space and time are connected. This is in space. In time, you have a very similar comment to do. In time, typically you have a limited frequency band for considering your phenomenon. If you have a frequency axis, you may have an input. This is an input, F input of your system in frequency domain. And this input may have a spectrum like this. 0, practically 0 after this bandwidth. And this could be 100 Hertz. After 100 Hertz, you have nothing as input. Okay? So, if you have an input like this, and for example, consider the perturbation and the input force disturbing an aircraft in flight. In an aircraft in flight, you have perturbation of the order of second. You have something harmonic of a frequency of about 1 Hertz, 10 Hertz, nothing more in terms of frequency. You don't have excitation at high frequency after 10 Hertz. 10 Hertz is something like this. You don't have a force exciting in time. Therefore, remember, the output in frequency domain is equal to transfer frequency domain matrix applied to the input f. Okay, and if this input f is equal to omega by 2 pi, if this input f is band limited, also if you have a frequency response function which is rich, this frequency response function could be composed by function like this. Okay, continuing in frequency, but when you take this product, this by this zero here definitely cancel the output. This output Q will be something like this, and then 0. So we are not interested to represent the dynamic after turn 100 Hz. Write this concept. We are not interested to represent the system dynamic greater than 100 Hz because the input is 0 after 100 Hz. Therefore, your system, which is an elastic system, in this case, note this F is not the aerodynamic, this F is a perturbation, external perturbation. So your elastic system can be represented within that bandwidth. And therefore, if you, inside this bandwidth, you have 10 mode, 10 structural number of frequency, you know the elasticity probably moves the poles of the system, but in general, the imaginary part of the pole remains almost the same after the aerodynamic contribution. So you can keep to estimate the frequency band of the system also in the presence of the air. Okay, so if your structural mode inside this band are 10 mode, you can use the first 10 mode. And this is correct in time, but this is also correct in space, because in space, this guarantee a good representation of the, in space, of the dynamics in that bandwidth. Okay? And this is very important. This is the answer to the question, why modal coordinate? We represent the elastic phenomena in modal coordinate because we are interested on approximating space our dynamics of the continuous system in a global sense, first of all, and we are interested to represent such a dynamic in a limited bandwidth as the input is limited. Okay? Space and time. Okay. Now, something more theoretical. Uncompressible, unsteady, potential flow. I promise to you to obtain this operator. An operator such that applied to, apart the dynamic pressure, applied to the modal coordinate will give us the generalized aerodynamic force as dependent on Q. And this allows us to close our aeroelastic loop. This is the structure. The structure is able to give you Q bar. Take Q bar, multiply Q bar by QDE, and then obtain the aerodynamic force as input for the structure. And this is my project. Okay? Now, theory. Thermodynamics. Some recap on thermodynamics. For continuum, and then fluids. The first principle to be stated for thermodynamics is the Clausius inequality. This is the most important law to be stated as principle. This states that if you have a continuum like this with a volume, you can define an internal quantity like the entropy is a scalar, namely is a scalar quantity. This is the entropy. You can define this quantity per unit mass. So a specific quantity. And if you take this volume, this is a material volume in the sense that this volume is placed by the same material. Okay? So it's a time varying volume. If you consider the total entropy in a time as the integral of rho is the density, the entropy in dV, this is the total entropy for the volume, for the material volume. The total variation of this quantity, excuse me, riesci sempre a beccarmi a lezione, complimenti. Alle 2, dopo le 2. Sì, ok. Come sono le 45? Ah, sì, dopo le 4, scusami. Ciao. Bye bye. Allora, the total time derivative, so the variation in time of this quantity is always positive, but maximum equal to another quantity related to the head flow vector. This is the head flow vector. And sorry for the notation. This Q is a non-physical quantity. These here are generalized variable. This Q is a physical quantity. Is the head passing in time per unit surface. So it's a watt per square meter quantity. Okay? And this is the head flux vector. Let me indicate this with an arrow as hat, okay? To distinguish this by this. This is a physical quantity. This is not, okay? So if you define this quantity here, the integral of the dot product of this quantity by the external normal to the surface is the hat passing on the surface, the unit surface, okay? But you have to consider not this quantity in the Clausius inequality, you have to consider this quantity divided by the temperature T. So the heat flux vector divided by the temperature in ds is representing the head flux divided by the temperature through the boundary surface of the body. The convention for the hat is that the hat is positive if is outward. So positive if outward means that it is positive. In Italian is calore uscente, is positive. And therefore, the derivative of the total entropy is always greater than or equal to the incoming inward minus sign, famous minus sign, head flux vector divided by the temperature. And this is the general way for stating the Clausius inequality. This is true. This has to be true for any choice of the volume at the limit for a particle. Okay? And again, this temperature is absolute temperature, and so is a greater than zero quantity. And this inequality is able to distinguish reversible transformation is when the equal sign is valid, and irreversible transformation if the strict inequality is valid. Okay? So this is the basis, the general basis of thermodynamics. I want to apply this for fluid. This is valid in general. This is a general, fluid and solid. No distinction. Okay? First of all, here, I want to localize this inequality. Localize means I want to apply this for a particle, not for a portion of the continuum. In order to do that, this is an integral on the surface, this is an integral on the volume. I'm sorry for the same letter. S is for entropy, and here S is for surface. So I write here surface. Oh, surface, surf. Okay? And apply the Gauss theorem. I want to, for applying a Gauss theorem, this integral, the integral of Q dot N divided by theta in ds is equal to the volume integral on V, this is on surface, of the divergence of Q divided by theta in dV. Okay? And so we have to develop this divergence. We can develop this divergence. And we have that the divergence of Q on theta is equal to 1 on theta divergence of Q plus Q dot gradient of theta. If you want to demonstrate this inequality, this equality, you can use the index notation and write this divergence like the divergence in terms of Cartesian component is equal to q, the derivative with respect to xi of qi divided by theta. I summation. This is the divergence. If you develop this derivative, you have 1 of theta derivative of qi with respect to xi plus qi derivative of 1 on q, which is equal to minus theta square. I am applying the chain rule. Chain rule means regola della funzione composta in Italian, o regola della catena nel resto del mondo, chain rule. And so you have minus theta square, which is the derivative of 1 on theta with respect to theta, and then you have the gradient of theta. Okay? And this is the development of gradient of 1 on theta this year. So at the end, I have this, and this is equal to this. Okay, so let me rewrite the inequality in another sheet here. The inequality is the following. We have rho ds on dt integral plus the divergence of q on theta dv greater than 0, but this has to be valid for all volume, possible volume of fluid, and therefore this is the localization. This is valid for only if rho ds on dt plus divergence of q on theta greater than 0, and after what we have developed, we have the following. We have that this inequality state that this quantity has to be greater than 0, rho ds on the theta plus 1 on theta divergence of q, okay, and minus 1 on theta square gradient of theta, which is this, okay, and this is greater than 0. Okay, at this point we have just to develop this quantity, here, which is the head flux divergence, and the head flux divergence is involved in the energy equation. Energy, or if you prefer, power, because namely this is an energy per unit time, so it's power or energy equation for a continuum, state that there exists an internal per unit mass energy typically indicated with E, such that the rho by dE in dt. So this is the power, because it's the derivative, time derivative of the energy. And for energy balancing, this energy time variation will balance in any time for a particle minus divergence of the flux, the head flux vector q bar, plus t dot dot t. Now, this energy balance equation is the standard equation you use, for example, for fluid dynamics or for motor cycle thermodynamics, when you say that the internal energy, like du, is equal to the head plus for a fluid, okay? This is the general form of this. This is particular, is a special case. I have no time for demonstrating to you this equation. This can be easily demonstrated. However, this is the energy balance. This is a special form of this, okay? So, actually, it is stating that if remember the flux q dot n is the head outward head, positive when outward, okay? So the divergence is the local concept of this flow outgoing or ingoing for a particle. When you don't have a surface but you have a particle, the flux through the surface becomes the divergence in a point. Gauss-Dodge. So these equations are actually stating in a point that the head flow incoming to the particle minus the divergence of Q incoming, not out in, plus the external work performed by all the other particles on the single particle, T dot dot D, for fluid, P dV, this mechanical work plus this thermal work are actually balancing the internal energy. This is the energy balance for a particle. Okay? And this energy balance will allow to express this quantity. Yeah. Okay? So, let's have a stop, a pause, and then we continue this discussion about the thermodynamics of fluid. Up to now, we have continuum body, not distinguishing fluid and solid at the moment. Okay? This is valid for any kind of continuum. E quindi voi vorreste venire in 4, sempre in 4 vorreste venire.
Sì. Eppure siamo due.
Eccoli qua. Vabbè.
No. Sulla slide precedente, quando all'inizio abbiamo fatto la definizione dell'errore, il modello nel quale si scelgono le coordinate modali.
Sì, ma io volevo chiedermi una cosa, ma mi sono dimenticato.
Sì, intendeva la prima che ha fatto il GPX e l'epsilon globale, il primo che ha scritto. No, eccola lì. Il primo in cima è l'epsilon globale, intendeva.
Sì, è globale.
Professore,
Sì?
scusi, io avevo provato l'altro giorno a fare il punto opzionale dell'esercitazione, quello di selezionare la condizione iniziale. Però scusi, cioè, non capisco bene come si potrebbe fare, perché comunque noi in condizioni critiche abbiamo comunque delle componenti su entrambi i modi, su entrambi i modi propri.
E chi l'ha detto? Lei può fare in modo che la condizione iniziale sia tale da poter eccitare solamente il modo quello stabile, non quello con l'altro.
Ah, ok.
Sto dicendo che lei può scegliere W0 e W0 punto, vettori, ciascuno con componenti 1 e 2,
Sì, sì.
tali che la C che moltiplica il modo critico di Flutter sia 0.
Sì, zero.
Lei ci vuole
Sì, sì, anche perché sto
scegliere.
rivedendo adesso sulle dispense, io mi stavo rifacendo sull'espressione, però qua già implica che la condizione è critica.
Lei
Sì, sì.
sicuramente ci riuscirà.
Scusi?
Lei sicuramente ci potrà riuscire. Una volta che ci riesce, però, la domanda più seria non è tanto chiederle se ci riesce a farlo, è questa, ma allora il sistema è stabile, perché mi dici che è instabile? Perché io do quelle condizioni iniziali e il sistema la risposta si mantiene limitata. Che cos'è che non sta funzionando? Forse non sta funzionando come io sto interpretando la stabilità. Forse non mi ricordo bene che vuol dire stabile. Perché sia stabile, che cosa deve succedere? Le basta che ci sia una condizione iniziale che le dà una soluzione limitata o di condizioni iniziali ce ne devono stare
Arbitrari.
tutto l'intorno, Liapona, stabilità secondo Liapona, tutto l'intorno, quindi vuol dire che lei non solo deve trovarne una, ma deve, perturbandola, deve poter...
Sì, una qualunque perturbazione deve tendere poi al suo valore, diciamo, di equilibrio.
Esatto.
Sì.
E succede così?
No, perché io mi vado a scegliere una condizione particolare.
Quindi non basta che... Cioè, chiarisca questa cosa e questo lo viene chiesto.
Ok, grazie.
Prego.
Quindi tu stai secondo sì, però in che posto sei? Provo l'assolvente valorale e
Ha fatto lezione ieri Marino?
fatto?
Lezione ieri Marino?
Sì.
Annalisa, scusa, una cosa al volo, perché sto durante l'intervallo, ho aperto un attimo la lettera. Non era il caso forse di dire la quasi totalità degli studenti della facoltà di ingegneria civile e industriale, invece delle facoltà della facoltà, ma si capisci? Ok, va bene, sì, sì, d'accordo. Va bene, pronto? Ok, va bene, sì, è caduta la linea come al solito, sì, sì. Quindi questa è già disponibile per le firme, Ok, vabbè. Va bene. Vabbè, ma... Sì, sì, certo, certo. Ma forse non era il caso semplicemente mandarla a un po' di persone da subito? Cioè, la devo... Ok. Il problema è io se lo mando come presidente del CAD ai miei colleghi, capito? Certo, ti pregherei di non chiedermi di... Cioè, io il 90% la firmerò, mi sa. Però meglio che non... capito? Figurati, non figurati, ma te l'avrei detto. Sì, sì, sì. Chi vede il file Excel delle firme? Lo vedi tu? Ci accedi? Ah. Fabio, sì, sì, sì. Ok, va bene. Ok. Mandala al direttore. Mm. 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 Mhm. Mhm.
Però non so quando uscite finito con l'evangelia era
Allora, ti dico che la Rosaria ha già fatto un casino, non mi sta facendo incavolare. Domani no, sta a fare un casino. Niente, che domani sposta, non fa lezioni, quindi vuole spostare perché l'ha già fatta e quindi voleva chiedere a De Sole di fare gli copigli di 2 ore di buco, invece De Sole ha detto che non può perché d'altronde io dice il giorno prima ha preso già l'impegno. Vabbè. No, adesso dicono domani, voglio vedere 2 ore di buco che fanno gli studenti, voglio proprio vedere che fanno. Sì, esatto. Ma magari se non andassero non facessero più lezioni con lei, però. Con mezza classe. Vabbè, senti, fammi andare che faccio quest'altra ora, ok? Grazie. Sì. Ciao.
Il corso è un pochino all'esame.
Allora, io avrei intenzione, it's my intention this year to involve you to a numerical model as soon as possible, and probably I will provide to you a finite element model for elastic analysis, and I give you this model, and so you will use this for elastic analysis later in the course. But at the beginning, the structural analysis should be possible, and so you could adopt and use this numerical model in advance to be ready for applying the aeroelastic analysis in a second time. I want to do this year, and I am organizing this issue. Okay. And now I want to go to the second part of the lesson. So we have the flux, the heat flux vector Q, the divergence, as given by the internal energy balancing here, and so we can rewrite this inequality in this way. We have rho ds dt, and then we have we can multiply. Look, we can multiply any term of this inequality by theta. So we have theta here, cancel this and cancel this. Note that this can be done because theta is always greater than 0, and so this multiplication does not change the sign of the inequality. And so we have rho theta ds on the t. Instead of this divergence, I have minus rho dE on dt plus t dot d, and then we have minus the gradient of theta. I forget something here. Yes, I have q. I have here. I'm sorry because when developing this at this stage, we have q dot gradient of theta. Okay, and so we have this dot Q. Okay? And therefore here we have Q dot gradient of theta, a vector divided by theta. Okay? So this is our final inequality. This is the Clausius inequality. And now we can just to say something about this quantity. And this is the stage for defining our state equation. The state equation is the equation defining a continuum to be a solid or to be a liquid. We have just to establish the dependence of the internal energy per unit mass as a function of something. And if you suppose to have this dependency on two scalar quantity, you have a fluid. This is the case of a fluid. In other words, when the internal specific energy is a function of two scalar quantity, you have only two information for defining the internal energy. And this is the case of the solid. In the case of the fluid, excuse me. In the case of the solid, this information is based on the knowledge of a scalar quantity and a tensorial quantity. So you have a higher order information because we are describing a solid. And you know the solid is able to keep the shape as trivial definition. And this is the point at this level, okay? So we don't want at the moment to describe the solid thermodynamic, we want to describe the liquid thermodynamic. And therefore, we want to choose two scalar quantity, one for the thermal part, another one for the mechanical part. So for the thermal part, we introduce the entropy as independent quantity, independent variable in your state equation, and we introduce the specific volume or the density, which is the reciprocate, the specific volume tau for the mechanical scalar quantity. Tau is equal by definition on 1 on rho. Rho is the density, and therefore tau is the specific volume, the reciprocal part of the density. Okay, so we are addressing to study fluid. We have already studied the solids in our life. That's all. Fluid, but it is fluid for elasticity, it's not fluid in general, please. So fluid means that this function is a function of S and tau. Therefore, when you want to take this derivative, you can develop this total time derivative as a part involving the first space variable, so as the partial derivative of E with respect to S by the total derivative of S divided by time. Okay? And this is the first contribution. And the second contribution, you have the partial derivative of E with respect to tau, and then the total derivative of tau with respect to time. So, developing this quantity in this way, I am assuming that I am working with fluid, not solid, okay? This partial derivative by definition are performed by keeping the other variable constant. So, you have to derive E with respect to S and then keep tau constant, and this is the derivative of E tau with entropy constant, of course. Okay, and I would like to call these two derivative, partial derivative, like E sub tau, this here, and this here E sub s. Okay? Okay, so let me write our inequality, including this part. We have the following. We have 0 rho theta ds on dt minus rho multiplied by E tau ds dt plus Es excuse me, yes, oh, excuse me, the opposite, E with respect to S is Es, this is E tau, I'm sorry. Es ds dt and E tau d tau in dt, okay, and plus t dot dot d, and here we have minus q dot gradient of the temperature divided by theta, okay, and look this for a fluid. This is a strange quantity. This is the derivative of 1 on rho in dt for a fluid. And by using the chain rule for the derivative, I have minus 1 on rho square, the derivative of rho with respect to the time. Okay? Continuity equation. You know very well that d rho in dt plus rho divergence of the velocity is equal to 0. Okay? And so we can substitute this derivative. And we have that this is equal to minus this is minus rho divergence of v by r, and so we have plus 1 on rho divergence of velocity. Okay. Okay, so let's put together this term with this term here, and look, 0 greater than rho theta minus Es ds on dt, and another step together, we have divergence of v. The divergence of v is equal the derivative of vi with respect to xi summation, right? And this is also equal to this, excuse me, okay, delta Kronecker ij, the derivative of vi with respect to xj. It is redundant. I see that this is a redundant notation, but formally this is identical, because the Kronecker delta is actually asking to you that this quantity is 0 when I is different by j, and is equal to 1 when I is equal to j. And so you have the divergence of V. Okay? But in absolute sense, this is very interesting because here you have identity dot dot d. Ta-da! Where d ij is exactly the derivative of v with respect to d is the strain rate tensor. D is the strain rate tensor and is equal to the symmetric part of the gradient of the velocity. The gradient, the symmetric part of a tensor has the identical, the diagonal part of the symmetric part of the tensor is equal to the diagonal part of the tensor, because the symmetric part in the diagonal term is identical. And therefore here, in this definition, here you have the velocity, the derivative of the velocity with respect to xj, but evaluated at the diagonal term. So you have identically this equation here. In this way, if I use this, I have the capability to put in common this factor with this factor here. This is the scope of this. Okay, let me show you. Here you have, look, minus rho, and instead of this, you have the one or rho divergence of V, one or rho and this rho cancelled, and so you have minus I dot dot D multiplied by E tau. Okay? So please, I have developed this term, this by minus rho. Okay, so this d tau in dt is equal to this quantity. Okay, and therefore here you have the divergence of the velocity. You cancel rho here and here, but the divergence of velocity is equal to I dot dot d. At the end of the story, I have minus E tau, here, E tau, by the derivative of tau with respect to t, which is I dot dot d. Okay? The last term is plus t dot dot d, and finally minus q dot gradient of theta by theta. Okay, very last point is 0 rho theta minus es ds on dt plus t minus E tau I by d dot dot d, and finally minus q dot gradient divided by theta. And so we have a sum of three terms, this, and this. The sum of this term has to be greater than 0 for any transformation. Okay. I want to focus our attention on all the transformations having each of these terms greater than 0. I realize that this is a subset of the general case, but this subset is not so distant from the total subset. The evidence in the lab are such that this condition is able to include all the experiences you may have for this kind of transformation. Okay, so we can focus, for example, on 3. The term 3 is minus q dot theta, gradient of theta on theta b greater than 0. This means that when you have an irreversible transformation, this quantity is positive. In the case of a reversible transformation, you have that q dot gradient of theta has to be less than 0. And this means that if you have a flux, a hat flux vector like this, you should have a gradient of the temperature here with an angle alpha greater than pi 2. And so this means that the head flux has to go from particle with a temperature lower with respect to the other particle. Okay, so this means that if the head flux go from here to here, this point here, the temperature is here, for example, 33,000 Kelvin, and here you have something lower, which is, for example, 2050 Kelvin. And this is imposed by the thermodynamics for fluid, but for solid is the same, as you know. Second part, this part here is very interesting. We have that T minus E tau I has to be dot D has to be greater than 0. So you have here something interesting, which is a new tensor. You have a new tensor. I can ask this tensor as T irreversible, which is equal by definition by T minus E tau I. Okay. In fact, if T irreversible is equal to 0, you have that this term is 0. You have that T irreversible dot D is 0, and so you have an irreversible transformation, as you know. A reversible transformation, excuse me. If this is 0, then this is 0, and you have a reversible. So the existence of T irreversible not equal to 0 is indicating the presence of irreversible transformation in your body. In dynamic of fluid, this tensor is also known as viscous tensor, SB. T irreversible is the viscous tensor for fluid. And therefore, and this viscous vector exists if and only if you have an irreversible transformation in the point of view of mechanical dissipation issues. Okay? Note that the total stress tensor T is equal to the total stress tensor is equal to T and is equal to T, something wrong probably, excuse me, let me check. Let me check. Yes. Okay. Let me check a point. Yes, okay. So this T is equal to T irreversible plus E tau I. And so this part of the tensor is the only surviving in the case of reversible transformation. So this is T reversible. So you have, in general, you have T as a sum of these two contributions. If you have strictly reversible transformation, this part is 0, and you have only this here. In other case, if you have a generic transformation, you have in the same time this part and the other. But look at this point. In the case you have this quantity here, we can have an interpretation for E tau. This E tau is a partial derivative, is the partial derivative of the internal energy with respect to tau at zero entropy. And we can give an interpretation to this scalar, and this scalar essentially is the pressure with an opposite sign. Why this is a pressure? Because in the case you have a zero velocity, for example, in the hydrostatic case, in the case of hydrostatic case, zero velocity, you have zero gradient of velocity, and so zero d. Okay, and when you have zero d, if you have zero velocity at zero d, you have no irreversible phenomena, because the velocity of the fluid is zero, you are at rest. And so the stress tensor in that case, T, is equal to minus E tau plus 0. And therefore, in that case, what about T? T is exactly the common definition of pressure. This is plus. And therefore, you have minus P I in the hydrostatic case. So P can be interpreted as the pressure. At the end of this story, we have that the term number 2, excuse me, I have not indicated this, the term number 2 is such that the stress tensor can be decomposed in the irreversible part, also known as viscous, part of the stress tensor, plus the reversible part, which is equal to minus pi. And this is the result of thermodynamics on the term number 2. Okay? After this position here. This is just a definition. I want to call pressure this partial derivative. The pressure is, minus the pressure is this time derivative by definition. As very final part, we have the number 1, term in my Clausius inequality. And in this number 1, we have that the term rho theta minus es, ds on dt, has to be greater than 0. Now the state space variable are 2. And here you have 1, 2, 3, 4 terms. You have the derivative of the entropy, which is a state space variable. You have this partial derivative, you have the temperature, you have the density. So how can you ensure this to be greater than 0? Okay, you cannot ensure this inequality by distinguish reversible and irreversible transformation. You may only have the possibility to define this partial derivative as identical to the temperature. This is the temperature. Okay, and this is the conclusion of our discussion of the Clausius equation. And after this part in thermodynamics of fluids, is imposing this discussion, which is imposing this constraint, excuse me, and this definition. This definition, which implies this constraint. At the end, we have two inequality constraints in thermodynamics, one of mechanical type, and this is related to dissipation mechanism, and this here, which is related to thermal conduction. How our head flux vector propagates in a fluid. The propagation is not intended as a convection, transport of particles, but propagation in the fluid. Okay? And this is not a problem as it is in the solid. For a fluid, the main means of head flux transfer is the motion of the fluid. It's not the conductivity of the fluid, of course. Okay. Okay. Now we are ready for discussing the state space equation. What is a state space equation? State equation, excuse me. State equation is a equation giving the internal specific energy as a function of entropy and specific volume. So what about this equation? I want to give you a provocatory definition of this for demonstrating to you that what you know on this issue is just a consequence of what I'm going to show to you. In fact, if you define in this way this function, if you say that the internal energy is equal to the exponent, I'm sorry for the use of E as for exponential, so I use X exponential of S, excuse me, of S, I want to stress the fact that this is the variable S minus S0 is a reference value for the entropy, divided by this quantity Cv is not curriculum vitae, is the specific head at constant volume, and divided by tau to the power gamma minus 1. Excuse me, this tau is again a function of, is the function for your state space equation, and then multiplied by Cv, excuse me, Cv divided by R. So this is my E as a function of S and tau. Okay, you may say, but okay, interesting. And what do you want to say to me? Remember that Cv and Cp are the specific head at constant volume, and this is the specific head to constant pressure, as you know. And once you have defined these two quantities, you may define a subproduct gamma as a ratio between Cp on Cv and R as difference as from Cp and Cv. Okay, are you familiar with this? Okay, now a lot of experimental men in the history of the thermodynamics has give as a final formula relating this quantity, this formula, and I want to show to you that this formula is actually giving to you the definition of perfect gas in a thermal and caloric point of view. This is the equivalent state equation for ideal gases. So I am presenting to you ideal gas as a gas having this state equation. You could not believe to me, but look what happens. Assume this. And force theta. By definition, theta is this. So theta is the derivative of E, internal energy, with respect to the entropy. Take the derivative of this quantity. We have 1 on Cv, the derivative of the exponential, and all the rest of the equation keep identical because S is only here at the exponential. And so you have 1 on Cv by E. And what is this? We have that the internal energy is equal to the specific head at constant volume Cv by the absolute temperature. And this is a first equation denoting a perfect gas in a caloric point of view. This is the equation for perfect, so-called perfect gas, calorically perfect gas. Okay? Perfect in the sense of het, calorically perfect. Okay? This is a first consequence. And I have used this. 1. 2. Pressure, the other definition. What about the pressure? The pressure, remember, is the minus the derivative of V with respect to tau. Okay? So, the pressure is minus the derivative of E with respect to tau. Okay, this is more complicated because we have tau here, but we can do. And we have the exponential minus E to the power S minus S0 by CV. And then we have CV on R, constant. And now I have to derive this. And this is the exponential. When you put this at the numerator, you have tau to the power 1 minus gamma. And then you have 1 minus gamma, multiplying by tau to the power minus gamma. Because you have 1 minus gamma, derivative, and so on. You have 1 minus gamma. Okay. Okay, if you look this again, you have gamma minus 1, the minus sign here, gamma minus 1 by E, the original E, divided by tau. Okay? Okay? And, but, remember, so we have P tau, you have this, P tau is equal to gamma minus 1 by E. But E is equal to CV by theta. CV by theta. And now look to this part here. We have gamma Cp on Cv minus 1 multiplied by Cv. And this is identical equal to R. Ah, interesting. What we have found? We have found the standard equation of perfect gas, thermically perfect. Okay? So with a unique formula, you are representing perfect gas. But this is the state equation for perfect gas. Okay? And so we have as a final result here, P tau is equal to R theta. So this gas is thermally perfect. Perfect. And therefore you have thermally and calorically perfect gas, and perfect in a unique word, ideal gas. Okay. Okay. Let me do another couple of content for our preliminary work on thermodynamics for fluid. Another interesting preliminary work is the following. If you have the energy equation, better the power equation. We mentioned this equation, power equation. Remember, we state that rho dE in dt, in derivative of the internal energy, is equal to the hat locally in a particle exchanged by the particle with the other particle. In other words, the divergence of the flow, the hat flow, plus T ddV. This is the energy balance. But now we can use all the issues we have developed for the thermodynamic of fluids, and this derivative is equal to the derivative of E with respect to the entropy for the total derivative of the entropy with respect to the time, plus the derivative with respect to the tau, and then we have the term involving, we have developed this term, and this is equal to the divergence of velocity. So we can develop this term as equal to, this is equal to the temperature, and this is equal to, remember, we have let me develop this in a better way. Here we have excuse me, the derivative is -1 rho square. We have done this. Let me find before. Okay, this here is equal to 1 on rho divergence of V. Okay, 1 on rho divergence of V is this. Divergence of V. Okay, and excuse me, by the derivative of tau with respect to the time, and all this was equal to okay, what is the final result? The final result was, help me guys to put together all the pieces. Okay. At the end, we have the following. We have this is equal. This should be equal to theta ds dt minus p on rho divergence of v. Okay, and where of course this p is equal to this derivative. Okay, and so if you substitute this quantity inside the internal energy, this quantity here, okay, you have that rho theta ds on dt, which is this term, is equal to minus the divergence of q plus, and you have the only viscous part of your tensor, because you have T minus Pi on divergence of T. Excuse me, plus probably, not minus, plus pi dot dot d. And this is the viscous stress tensor. And this equation is very important because this equation is representing the conservation of the energy in terms of entropy. And this equation is saying to you that because of energy conservation, the entropy, the derivative of the entropy, may be positive or negative because of the flux of the head, or because of the viscous effect of the fluid. Okay? And so the entropy may grow because of the head, but also of head incoming, going inside the particle, or because of dissipative mechanism. This is the first cause, the entropy increase because of head going in or dissipative mechanism. Okay? And I stop now, and we continue tomorrow, and we apply this concept for defining a steady potential flow. Okay? We recap all the main concept, and we start to talk about a steady potential flow. And we first study the uncompressible case and then the compressible case. And thank you.